Okay, so now we're going to talk about the second part of the analysis section here, which is the binary analysis, and it says that it generates the XY, PXY, and gives free energy of mixing curves for binary systems. And this is one of the things that are very important, and we use them a lot in cases like flash separation and for distillation, so we can know how easy the separation will be, how many stages we would think we need in case like this. So let's say we have two components like ethanol and methanol, and we want to plot the TXY diagram. So for the TXY diagram, the y-axis is the T and the x-axis is x and y. And the bases would be either moles or mass. You can pick whatever you want, and the x-axis would be the percent of ethanol or methanol. You can pick whatever you want. I'm gonna make it methanol, for instance. And here you can pick how many points you wanna use. So you can use from 0 to 1 with interval of 50. And of course, you are selecting one of the components that you already selected here in the component section, and you can do or draw the diagrams for more than one or at more than one pressure. So here I can say it's one pressure and 1 atmosphere, and I can put it at 5 atmospheres, and then I will run the analysis. And when the analysis runs, so it's doing calculations again. Before looking at the plot, I want you to think of how many calculations are done. So we are doing the bubble and dew point calculations 50 times for two pressures, so it's gonna be like 200 calculations, which is a lot. And again, the results here, you can see the plot for the TXY and TXY for ethanol and water. I might be interested in this region, so I can zoom in just to take a closer look at the at this part closely. So this is one nice thing. Again, if you're interested in the results, you can get them from here. And this is going to be useful because in some cases you might be interested in the XY diagram, like the McCabe-Thiele diagram. You want to get the XY diagram to plot the or draw the number of stages. So in this case, you're not interested in the temperature, you're just interested in X and Y's. And this is something you can get here, which is the liquid mole fraction and the vapor mole fraction. You can get it for the more volatile component for ethanol, or it's going to be for methanol. Um, and this is the X and the Y's and the X for methanol and water. The nice thing, you can find the K values, so you can see these are the K values for ethanol and for methanol, and you can easily see that the values are higher for methanol, which means that methanol is going to be richer in the vapor phase. So methanol is the more volatile component. Um, and this is nice thing. Let's do the analysis for ethanol and water, and let's run the analysis and take a look at it. Again, it's recalculating everything, and you can see that the plot looks different, and this is because we have an azeotrope in the ethanol water mixture. Let's keep it for the 1 atmosphere. So I'm gonna make the maximum value here like 105, and this is something that we can easily set from here. In the format tab, you can make the maximum 105 and the minimum 75. um, and here you can see I'm now limiting my plot only to this part, and there looks like something is here like an azeotrope. And let's zoom in here just to take a closer look. Yeah, we have some azeotrope here, and it looks like the two plots are kind of overlapping, but they're not actually overlapping. They are very close to each other. The overlap happens only in one point. And again, we can take a look at the results and see the X and Y values here, and this is from the graph, it is around 0.15 mole fraction of water. So this is the mole fraction of water. It's gonna be something around here, and you'd see that this value and this value, which is the liquid mole fraction, is almost the same here. It is kind of different here and kind of different, or it's kind of close. So to get the azeotrope, you need to figure out which point is exactly giving the same value, and this is gonna be the closest thing. So the azeotrope would be something around here. We will see in one of the future videos how we can get the azeotrope exactly from Aspen Plus, but it's not gonna be. We cannot do this here. We can do this in Aspen Plus itself in the simulation environment. Um, so this is for plotting the phase diagrams. Again, it's very helpful and useful, and it gives real results. It's not just giving any fictitious or ideal results. You can draw the XY diagram here. Um, uh, from this, it's at 5 atmosphere and can 1 atmosphere. Again, you can pick which one to display. So I can I don't remember where the variable lines. We can delete the 5 atmosphere and keep only the 1 atmosphere. So this is mole fraction water and vapor fraction water. Of course, this is not the shape that we are used to, because this is the less volatile component. We usually draw this for the more volatile component. That's why we can plot it for the more volatile component if we want. I think this is something we can do, that make the component ethanol instead of water, and this is how it should look like, and this is exactly how the XY diagram for water ethanol system looks like. And again, this is what the problem that we face when we do the distillation, because in this region we will have pinch point. There is no driving force, and in this region you'd see that at this point exactly you can tell that this is the azeotrope. It's around 895 89.5 mole percent of or mole percent of ethanol, and this is where the azeotrope takes place. So this is one nice thing that we can do. Again, there are more plots that we can draw. Besides TXY, you can plot TX by itself. You can plot the K values, which is a good indication of the volatility, and this is how it changes with the temperature. I mean, with the mole fraction. Sorry, as the mole fraction changes, the K values it changes, and this is all. You can play around with this and kind of explore more, and I think this is enough for this video, and I'm gonna see you in the next video, inshallah. Goodbye.